Okay, so we're broadcasting already, but we'll just wait a minute or so until the participant numbers will go up.
Mm-hmm.
Yeah, they're climbing up very fast right now. So maybe one more minute. So I'll wait till like basically 200 participants, and then probably it's a good number to go ahead. Okay, so and Senthil, so I'll just try to read off the questions maybe periodically.
Okay.
But I'll try to interrupt very few times, maybe like two times or so, and keep the questions mostly for the.
Yeah, either way, I'll leave it to you to decide how to do it. I'm
Okay.
open.
Okay, so maybe we can slowly start. So okay, hello everybody. Welcome back to our Frontiers of Light School, and so we have 2 more days to go into the conference, and I also wanted to remind you that today in the evening after the first 2 talks, we'll have also another hot topic sessions with short talks by students and postdocs. Okay, so today it's my pleasure to welcome Senthil Todadri from MIT to give a theory talk on topology and correlations in graphene materials. And please write down the questions in the Q&As. So if I see some questions, I periodically will try to raise those questions with Senthil. And other than that, I think I'll open the floor to you, Senthil, and thanks very much for participating in our conference.
All right, so wonderful. Thank you, Dima, for the introduction, and thanks to all the organizers for putting this school together, and also to Moiré and Rob for all the wonderful work in making this school run smoothly. It's been great. Attended several of the talks myself, and I've learned a tremendous amount. Yeah, so I'm looking forward to telling you about some of my thinking on this problem. So let me start by mentioning some recent collaborators with, who played a crucial role. So Yahui Zhang was my graduate student who graduated last year and is now a postdoc at Harvard, and 2 of my current students, Dan Mao and Jihon Dong, have been working on questions related to Moiré systems. And some of what I have done is done very close, in close collaboration with various postdocs, Adrian Poe, who's still at MIT, Cecile Repelin, who has become a faculty member in France, in Grenoble, and Debanjan Chaudhary, who's now a faculty member at Cornell. And I've had very stimulating collaborations with some of the experimentalists. Pablo, in particular, talked to him quite frequently. Very inspiring to talk to Pablo. And with Feng Wang at Berkeley and David Goldhaber-Gordon at Stanford. Okay, so one of the advantages of speaking in the middle of the second week of the school is that everyone has seen this slide before. Uh, so, uh, uh, so magic angle twisted bilayer graphene since 2018 has, since these papers by Yuan Chao and Pablo and their collaborators, has gotten a tremendous amount of attention. All kinds of beautiful things have emerged. So, so I'll rush through the slides since um, so the key point is that in these nearly flat bands that emerge near magic angle and twisted bilayer graphene, in this initial experiment by Pablo's group, they see a correlated insulator at partial filling of the bands. And near that correlated insulator, they see superconductivity and uh, uh, and the same essential phenomenon is uh, seen subsequently in very nice experiments by Andrea Young and Corey Dean. And in this beautiful result from ICFO from Demar's group, uh, where the superconductivity extends in a wide range of doping punctuated by insulators and so on and so forth. Um, so, um, so one thing that I want to immediately emphasize is that there are many routes to getting nearly flat Moiré bands in graphene. So one route is to take an N-layer graphene system and twist it to a magic angle relative to another M-layer graphene system. So the experiments that you've all seen in the previous slide, I'll refer to as the classic Moiré graphene system. So it has n equals 1, m equals 1. So this is the regular twisted bilayer. And there are other recent experiments where n and m are not 1. For instance, twisted double bilayer. There are a few papers on the archive, and some of them have appeared. In fact, 2 of them, I think, appeared in last week's issue of Nature. And there are other systems as well, where NS1, MS2, monolayer twisted on double layer has been studied recently, and so on and so forth. Now, the other route to nearly flat Moiré band in graphene is to take N-layer graphene and align it as closely as you can with the hexagonal boron nitride substrate. And in this case, the slight lattice mismatch between graphene and the boron nitride leads to a long period Moiré pattern. And correlated electron physics in this kind of system was first demonstrated in ABC stacked trilayer graphene aligned with boron nitride in beautiful papers by Feng Wang going back nearly 2 years now. I'll describe some of the results in this system as we go along. So there's many amazing things that have been found in Moiré graphene materials since Pablo's original announcement. So in classic twisted bilayer graphene, we have the correlated insulator and the superconductivity. It turns out that the transport in the normal state above the superconductor is also very interesting. There's a nice regime of linearity resistivity that whose origin is being debated. Now, if you further align the nearly magic angle twisted bilayer graphene, if you further align it with hexagonal boron nitride, people see ferromagnetism and in some experiments, a quantum anomalous Hall effect. Okay, and in the ABC trilayer graphene aligned with boron nitride, Feng's group demonstrated that the correlated insulator can be tuned at fixed electron density, can be tuned you can either tune in or tune out to the correlated insulator by using gates, in particular by using a perpendicular displacement field. And in subsequent work, they showed that you can tune in and out of Chern insulators with perpendicular displacement field. Ferromagnetism is seen, and there's some suggestion, at least there's some suggestion that the signature of superconductivity, but that it remains to be confirmed. In twisted double bilayer graphene, there's clear evidence for a spin polarized correlated insulator. There also was, at least initially, a suggestion of superconductivity but that again needs to be scrutinized and re-examined. So we don't really know if it's superconducting or not. Now, twisted bilayer graphene, twisted relative to monolayer graphene, has been studied very recently in the last few months. And once again, there's evidence of ferromagnetism and an anomalous Hall effect, which is probably eventually going to be a quantum anomalous Hall effect. So, all kinds of interesting phenomena in solid state physics that's been discussed over the years are now seen to happen within the single family of highly tunable systems. Okay, so some questions that one could ask, or how should we think about the three of the major phenomena that have been reported, namely the correlated insulator, the superconductor, and the ferromagnetism, and perhaps some of the other things that we already know about from experiments. Right? Now, I'm a theorist, so the natural question for most theorists is to ask, a first question is to ask, what are the important ingredients that we have to incorporate in modeling these systems theoretically, right? We want to build, models that are simple enough that we can say something about them, but are realistic enough that they don't throw out the essential physics. And a question that repeats itself in this field right from day one is whether there's a replay of the cuprate-like story, but with a different lattice and with more degrees of freedom. Maybe experimentally you can tune things, but fundamentally from a conceptual point of view, this is just another version of phenomena that we know from other correlated solids. Okay, so my plan for the talk is the following. Since I was encouraged by the organizers to spend the beginning of the talk in some kind of review, I'm going to start by giving my perspective on what fundamentally, from a conceptual theoretical point of view, is new about Moiré graphene as compared to other, correlated solids that we've encountered in the past. And the answer to me is that Moiré graphene forces us to confront the problem of dealing with electron correlations in a partially filled topological band. So I'll elaborate on this as we go along. Next, I want to talk about the limit of strong interactions and at total integer fillings, where we'll see that there's a very strong and very good reason to expect an insulator which has some sort of ferromagnetism built in. So then I want to move on and talk about how whatever theoretical understanding we have of this limit relates to experiments, and we'll see that the comparison with the experiment is actually very encouraging. And it's encouraging enough that it makes us a bit more ambitious and subject ourselves to an evaluation on whether the understanding in this limit really is what's going on in the experiments or not. So I feel like it's about the right time to not just stop with this encouragement, but to ask ourselves some tough questions. Okay, and this will then lead me to say very quickly about, very briefly, about some of the things that we may expect in the more realistic situation where we are not at not so strong coupling, and ask what are the things, what are the kinds of phenomena that we might expect. So this entire talk, I'm going to focus on correlated insulators and their magnetism. I'm not going to discuss the superconductivity very much. It's in this field, it's actually extremely tempting to think about the superconductivity and to talk about it. I'm going to resist that temptation in this talk because, at least theoretically, it's talking about the superconductivity is a bit more, is probably much more of a gamble than it is to talk about the insulator itself. So, and since this is at least partly a school, I'll resist this temptation to talk about superconductivity and focus instead on correlated insulators and their magnetism. You know, as theoretical strategy, I think it's much more likely that we will be able to sort out what's going on in the correlated insulators earlier than we are able to sort out what's going on with the superconductivity. So let's develop some confidence that we actually understand the correlated insulators before talking too much about the superconductivity. Okay. All right. So I'm going to start with a very brief primer on correlated insulators, magnetism, and superconductivity in other solids. As I said, these are the three topics in Moiré graphene that we would like to understand. So let's see what the standard story is in other solids. Okay. So I think everyone listening in to this talk knows what a Mott insulator is. That's the most famous correlated insulator. It's an insulator due to the jamming effect of Coulomb repulsion in a solid where the Coulomb cost of two electrons occupying the same atomic orbital, usually referred to as a Hubbard U, is so big that electrons can't move. If you're at, say on this lattice, each site is occupied by an electron. Now, it's been understood since Bill Anderson's work in the 1950s that the Mott insulator gives rise to some sort of magnetism because there's free spin at every lattice site where an electron is localized. And the standard story, which Anderson explained, is that if you treat the electron hopping in perturbation theory, then this anti-aligned spin configuration allows virtual hops to neighboring sites. So you favor antiferromagnetic interaction of neighboring spins. Indeed, the most common form of magnetism in insulators is known to be antiferromagnetism due to this mechanism. And it's, in fact, very, very hard to, but not impossible, to get ferromagnetism in insulators. There is a delicate mechanism that was worked out in the 1960s by Goodenough and Kanamori. It has to do with super exchange path with 90-degree bonds and so on. It's rare, and it gives, if at all it gives ferromagnetism, it gives very weak ferromagnetism. Okay, so that's one lesson we learn from textbook solid state physics, that correlated insulators go hand in hand with antiferromagnetism. Now, this picture of the Mott insulator is a real space picture. We think about the electrons as particles, and we should contrast this with our standard understanding for metal, which is a momentum space picture. We think of filling of Fermi surface, and we treat the electrons as waves. So, in the vicinity of the transition from metal to Mott insulator, which again in the context of Moiré, people are able to control how close you are to the correlated insulator and tune in and out of the correlated insulator. So it's natural to ask about what we know from other solids about the vicinity of the metal to Mott insulator transition. There, neither particle nor wave point of view is necessarily superior, and all kinds of interesting things happen. And perhaps the most striking phenomenon is high temperature superconductivity. So the classic examples are, of course, the cuprates. So you start with the Mott insulator and you dope, and you get high TC superconductivity. But superconductivity near the Mott insulator happens in many other examples as well. Here's the phase diagram of quasi 2D organic salts on lattices that are roughly triangular. Here the phase diagram is tuned with pressure, and at ambient pressure, many of these systems are antiferromagnetic Mott insulators. And then with pressure, there's the metal insulator transition, and the metal at low temperature becomes a superconductor. Okay, And here's another phase diagram of a different system, cesium-3 C60 buckyballs in an FCC structure. And again, at ambient pressure, these are Mott insulators. In fact, they are highly frustrated magnets with low ordering temperature, well below the Curie temperature scale. But then under pressure, there's a Mott metal insulator transition, and there's what looks like a superconducting dome with actually a sizable TC of 30-something Kelvin. Okay, so there's many examples of superconductivity near a correlated insulator in solid-state physics. So it's natural to ask whether Moiré graphene is another example of the same story, right? So there's an insulator which in Pablo's original paper was denoted Mott. These days, people refer to it as a correlated insulator. But it's clearly an insulator that's driven by electron correlations, and you dope it and you see superconductivity. So is it the same story or not? So let's think a bit more about what happens in a typical correlated solid, right? So typically, there's some set of bands that we'll call the active bands, which cross where the chemical potential lies, and they're separated from other bands that we don't care about. And if the interaction strength is much smaller than the gap to these remote bands, then it's reasonable to project the interaction to the active band to obtain an effective model in the block basis. Right? So that will take the form of a Hamiltonian which has some dispersion, which describes the band structure, and an electron-electron interaction where this U is what results from projecting the interaction to the active bands within this block basis. And I've suppressed spin or orbital indices which may exist in real materials. And in addition, we had to include phonons, we had to include impurities, and that's it, right? So that describes the typical correlated solid. Now, if you want an interacting effective lattice model, like a Hubbard model, what you do is to transform from the block basis to the one-year basis by defining this lattice Fourier transform. You take the block function of each k point and do this lattice Fourier transform to get the one-year function. And for ordinary bands, like say it describes the cuprates or the organics or something, well-localized one-year functions that transform nicely under the microscopic symmetries can always be constructed. And in this one-year basis, the free particle part of the problem can be replaced by a tight binding model, and then the interactions become some sort of, will become interactions that can be represented as real space interactions. And we then get an effective interacting lattice model. So this is the theoretical basis for a Hubbard-like description of, say, the cuprates or something like that, okay, or the organics for that matter. Now, in Moiré graphene materials, as we'll see, some Moiré graphene systems fit the standard framework, but the vast majority do not. And the reason is that there's topology of band structure, which prevents the passage to a nice one-year basis. So at least theoretically, the answer to the question that I posed a few slides back, whether this is a repeat of the cuprate story, at least theoretically, it's clear that it cannot be, and that the eventual understanding has, when all the dust settles, the eventual understanding cannot be within the same framework that's used to describe other typical correlated materials. Okay. So next, let me give a very brief primer on topological band theory. I'll be extremely brief and only discuss those aspects of topological band theory that are needed for the rest of the talk. Now, in two space dimensions, which is the only thing we are concerned with in Moiré graphene, the most famous topological band is the Chern band. For an isolated band in 2D, the total momentum space magnetic flux, the integral of the Berry curvature, is quantized to be 2 pi times Cn, where Cn is an integer known as the Chern number. And the Chern number counts the number of Berry magnetic monopoles inside the momentum space torus, and it's a topological invariant, and bands with different Chern number or topologically distinct. So this, of course, has been known since the 1980s. Now, if you have a material with a filled Chern band, that's what we call a Chern insulator. And a Chern insulator has this wonderful property that it shows an integer quantum Hall effect, where the quantization of sigma xy is proportional, is given precisely by the Chern number, right? And this requires broken time reversal symmetry. And as we know from the standard integer quantum Hall effect, if you have edges, then there are chiral edge states and so on and so forth. Okay. Now the aspect of these Chern bands that's important for us is that Chern bands provide an exception to this ability to go to represent the band in terms of one-year functions. And there's a theorem that was proven by Bruder and other people, Mazzari and so on, in 2007, that exponentially localized one-year functions cannot be constructed for Chern bands. And the intuition is actually very simple, that since the Chern band encloses a magnetic monopole in momentum space, it means that the phase of the block wave function cannot be globally well defined in the Brillouin torus. So the integral, the integrand in the k-space integral that defines the one-year function is not smooth. And this lack of smoothness is what prevents us from defining well-localized one-year functions. So a corollary to this is that a correlated partially filled Chern band cannot be simply described by an effective lattice model unless we do other things like introduce extra auxiliary bands, thereby increasing artificially the number of degrees of freedom to cancel the Chern number. But then we are working in a much bigger Hilbert space than we need to define the problem, right? And that increases the complexity of modeling the system. Now let's generalize the statement to symmetry protected band topology of the kind that has been studied intensely in the last 15 years. So I'll just illustrate this with an example that will actually is all we'll need for the talk. So suppose I have two active bands, a system where there are two active bands with equal and opposite Chern number, right? And I'll assume that the number of electrons within either band is separately conserved. So there's a global U1 cross U1 symmetry. One U1 corresponding to conservation of electron number in this band, another U1 for conservation of electron number in the other band. Then the band topology is protected by this combined U1 cross U1 symmetry, right? So the net Chern number of these bands taken together is 0. But so long as we have the separate U1 cross U1 symmetry, there is band topology in the system, right? So since the net Chern number is 0, you might imagine, and indeed is true, that you can construct localized one-year functions. But these localized one-year functions come with a price, and the price is that these functions are necessarily mixtures of states of the two bands. Okay, you cannot construct one-year functions that only involve block wave functions within a single band because this is a Chern band, right? So to construct one-year functions, you have to hybridize states from this band with states from that band, right? Now, so you could do that, but then the action of the global U1 cross U1 symmetry will be complicated, right? So these one-year functions will not transform nicely under this global U1 cross U1 symmetry, right? So lattice models of the system with such topological bands are dangerous unless we add extra bands to cancel this band topology. And they're dangerous because they're hard to treat while being completely faithful to U1 cross to the microscopic U1 cross U1 symmetry, right? So we lose our control on what the symmetry is doing if we try to make a lattice model, and it's very hard to keep track of it because it will be realized in some complicated non-local way. Okay. Now, there is a special topological flat band which everybody knows and in which strong correlations have been discussed for a long time. And that's a single Landau level and the phenomenon of the quantum Hall effect. So a single Landau level is a very idealized case of a Chern band. It has flat energy dispersion. Landau level is completely degenerate. the single particle states are completely degenerate. It also has a flat Berry curvature. So the Berry curvature is not distributed. It's distributed uniformly within this within the special Chern band. So as we know, strong correlations at partial filling give rich physics of the fractional quantum Hall systems. Probably one of the most beautiful traces in quantum condensed matter physics. But we do not understand the quantum Hall effect in terms of lattice, the tight binding models, but we do other things. We work with wave functions, we do effective field theory, and so on and so forth. Now, so the quantum Hall effect occurs in this situation where we have partial filling, where we fill this very special Chern band. Now, how to deal with strong correlations away from the special limit, the Landau level limit of a Chern band, or for other topological bands, is mostly an open question in many body physics, right? So as you'll see, it's this mostly open question that we have to confront in many Moiré materials, okay? So with that introduction, let me go on to talk about topological bands in Moiré graphene.
Senthil, just maybe one question from the audience, which arose before we go to the next part. So Antonio Manesco is asking, is it always possible to cancel Chern numbers by introducing extra bands, or is it just the case for fragile topology?
Oh, it's always possible. You just add an auxiliary band with the opposite Chern number. That's it. Yeah, that has nothing to do with fragile topology.
Okay.
Other questions?
No, this was it.
All right, very good. So let me go talk about topological bands in Moiré graphene systems. And so some of what I say may have a little bit of, will actually have some overlap with the nice talk by Andre Bernewig last week. And this part of the talk, perhaps to a lesser extent, with the talk by Ashwin and Alan MacDonald. But again, that's the advantage of speaking in the second week. I can, the second time people say something, maybe they understand it at a deeper level than the first time they see it. So let me just jump right in. So let's ask the very general question of how we should model these diverse Moiré graphene systems. So I want to discuss all these Moiré graphene systems together and as much as possible before specializing to any one. So as always, the structure of the microscopic Hamiltonian is that there'll be some band dispersion and there'll be some interactions, right? So, so let's start by understanding the symmetries of the problem, both the exact symmetries and the approximate symmetries. Okay, so let me first review some features of the band structure. So in Moiré graphene, the active flat bands near each of the two microscopic valleys of the underlying graphene system are disconnected from each other. So for instance, in twisted bilayer graphene, you have two mini-Brillouin zones corresponding to each of the two microscopic valleys of the underlying graphene systems. And these two the bands in these two mini-Brillouin zones are disconnected from each other through energy gaps that separate them from the rest of the spectrum. Now, in many Moiré materials, we can isolate the valence band from the conduction band within each valley. Within this mini-Brillouin zone, we can isolate the valence band from the conduction band. But this feature is not true for the classic twisted bilayer graphene, where for each valley, the conduction valence bands are connected by Dirac points. And this has to do with the symmetry. So the symmetries of the band structure, the obvious symmetries in the problem are charge conservation, and the extent that we can ignore spin rotation, the extent we can ignore spin orbit coupling, spin conservation, and time reversal is obviously a symmetry. Now, every other symmetry is approximate to various degrees, but many of these are excellent symmetries. For instance, Moiré translation itself is, strictly speaking, an approximate symmetry, but it's such an excellent symmetry that at low twist angles that uh, 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 we don't need to worry about this not being exact. For twisted bilayer graphene, a similar excellent symmetry is C6 Moiré lattice rotation. And the Dirac points within each valley of twisted bilayer graphene are protected by C6 cubed times T, which is C2T, a C2T symmetry. And if the C2T symmetry is broken, then generically these Dirac points will be gapped out. Now, this is nicely illustrated if we take twisted bilayer graphene and align it with the boron nitride substrate. The boron nitride explicitly breaks C2 symmetry, and that leads to C2 symmetry breaking for the graphene electrons as well, and that then leads to a gap at the Dirac points and to insulating behavior at charge neutrality. Now, it's interesting to ask about excellent symmetries, the full many-body Hamiltonian. Now, the fact that the two Moiré below zones near each microscopic valley are disconnected means that the separate conservation of charge and spin of electrons in each valley. This in terms of what this conservation law means for the symmetry, it means that there is a continuous global symmetry of U2 cross U2. So U2, there's a U1 part of U2, which is charge conservation, and there's a U2 part, which is spin. So there's a U2 cross U2, which is which represents the separate conservation of charge and spin symmetry. And this symmetry is broken by a weak intervalley Hund's coupling to U1 charge times U1 valley times the U2 spin. Now, it's important to recognize that even at the level of the single particle physics, there is no SU4 symmetry in this problem. People often familiar with ordinary graphene and say a magnetic field may know that there's an SU4 spin valley symmetry. But here, already at the level of the band structure, this SU4 spin valley symmetry is broken. Rather, this is all we've got. Okay. Now, so as I advertised, these bands have topology. Now, in twisted bilayer graphene, and this was discussed in Bernevik's talk quite a bit, the Dirac points within each valley have the same chirality in contrast to what happens, say, with Dirac points in conventional monolayer graphene. And this feature is indicator of a subtle form of symmetry-protected band topology known as fragile band topology, which can be trivialized to an atomic insulator by adding extra trivial bands. So this chirality, so within each valley, the fact that the two Dirac nodes within a single valley have the same chirality. So that is true, but opposite valleys, since they're related by time reversal, have opposite chirality. So this means that in this system, there's an obstruction to constructing fully symmetric one-year states. It's a bit like this example of symmetry-protected band topology that I discussed earlier in the talk, but it's more subtle because the topology is this subtle kind of band topology, namely fragile band topology. So I'm not going to discuss this much more here. There's a bunch of papers, apart from our own papers, Bernevig and Bernevik's work, which you heard about last week, and nice work by this group from Korea, led by Boom Jung Yang, and several other papers subsequently. Now, so though twisted bilayer graphene may have the subtle kind of band topology, in a number of other Moiré graphene systems, it turns out there is band topology, but it's a much more familiar kind of band topology. And simply that the bands have Chern number that is equal and opposite for the two valleys. Okay, so we demonstrated this for a number of different Moiré graphene systems. A nice example is ABC trilayer graphene on hexagonal boron nitride, aligned with hexagonal boron nitride. Here, it turns out that the band topology actually changes as a function of a perpendicular displacement field. For one sign, the bands are topologically trivial, while for the other sign, they're topologically non-trivial. And at the level of naive band theory, based just on the continuum model of Bitsitzer and MacDonald, you find that the bands have Chern number plus minus 3 for one sign of the perpendicular displacement field, while for the other sign, the bands have Chern number 0. Now, twisted bilayer aligned with hexagonal boron nitride, where you gap out the Dirac points, the bands have Chern number, and they have Chern number plus minus 1. In twisted double bilayer graphene, the bands have Chern number plus minus 2, and so on and so forth. So in all these cases realize actually exactly the situation that I discussed earlier in the talk of the example of symmetry protected band topology, where there are two bands with equal and opposite Chern number, and where the number of electrons in each band is separately conserved. So just like as we learned in that example, there's obstruction to writing down one of your functions that preserve the value U1 symmetry. Now, there's a word of caution about this analysis. As many people have emphasized, both at this meeting and earlier, interactions can renormalize the band structure. And in principle, we have to take that renormalization into account in asking even about the band topology. And so there's one example where this definitely plays a role, which is an ABC trilayer graphene. So there one can argue that one can show that the interaction with a remote occupied band can not only renormalize the dispersion, but also can change this Chern number from plus minus 3 to plus minus 2. So just like interactions can renormalize the band dispersion, they can also renormalize the band topology, and that should be kept in mind. Okay, so I want to give two illustrative examples of this phenomenon, starting with ABC trilayer graphene on boron nitride. And I'm going to discuss this, in fact, both of these within a simplified model to bring out the essential physics. So trilayer graphene has this kind of, ABC trilayer graphene has this kind of stacking, AB, AB, AB. And the first experiment showing correlated electron physics in this system it was by Feng Wang, published here. So what this paper showed was that you can tune, there's a gate tunable correlated insulator. So what was done was to have a dual gated sample in which you can control both the bottom gate voltage and the top gate voltage. So marching along this direction tunes a perpendicular displacement field, and marching along this direction tunes the electron density. Now in the band structure in this system, there is a single isolated band per spin per valley. And a remarkable feature of this system is that you can control the bandwidth simply by tuning this perpendicular electric field D. Now, the strength of the Coulomb interaction is mostly set by the size of the Moiré spot, and that's more or less unchanged as a function of the displacement field. This means the ratio of Coulomb interaction to bandwidth can be tuned simply by tuning the strength of D. Okay, so you have electrical control of the strength of correlations, and this nicely demonstrated in the system. So this line here is charge neutrality. And bright means it's highly resistive, and dark means it's metallic. So if you look, for instance, at half filling of the, or quarter filling of the valence band, at zero displacement field, it's metallic. As you increase the displacement field in either direction, it becomes highly resistive, indicator of an insulating state. So when we looked at the band structure of this system, as I said earlier, what we found is that for one sign of D, each valley filtered band has Chern number plus minus 3, while for the opposite sign of D, the valley filtered bands have Chern number 0, even though in this case there's still a non-zero Berry flux density. It's just that its integral is 0. Okay, so this system, you have this amazing ability to control both correlation effects and band topology very simply by changing the displacement field. Right? So the magnitude of the displacement field controls the correlation effects, and the sign of the displacement field controls the band topology. Right? It really is a wonderful system. So let's understand this claim. So pristine ABC trilayer graphene has a cubic band touching to a good approximation. Monolayer graphene has a linear band touching. AB stack bilayer graphene has a quadratic band touching to a good approximation. And ABC has a cubic band touching. So it's represented by an effect. So the vicinity, so the two bands that touch can be described by a two obviously by two band model. With off diagonal elements in momentum space, or kx minus iky cubed, and the complex conjugate in the other off diagonal. Now, when you turn on a vertical electric field, that acts like a mass term to this Hamiltonian. So these two diagonal matrix elements are equal and opposite. Now, the mass term means that this that the Berry face associated with this cubic band touching, where the cubic band touching has a phase winding of 6 pi when you go around it, of 3 pi when you go around it. So that phase winding is spread out once there is a mass that's turned on. So this Berry curvature that used to be a delta function at the band touching is now distributed in a small region of K space. But opposite valleys have opposite Berry curvature, and in pristine ABC trilayer graphene, these will cancel each other to give a net band with 0 Chern number. Okay, so the point is that in pristine ABC trilayer graphene, without alignment to a boron nitrate substrate, the two valleys are connected to each other through the bottom of the band, and so the band that you define, the Berry curvatures from opposite valleys will cancel each other and will give you a net 0 Chern number. So what's different about the Moiré graphene, about the Moiré system, is that the Moiré potential detaches the mini band near each valley from the rest of the spectrum. So then we can talk about the Chern number of each mini band. Without this Moiré potential, it's meaningless to talk about the Chern number associated with a single valley, because each valley is not disconnected from the other valley. But once we have this disconnection achieved by the Moiré potential, then it's sensible to ask about the Chern number of each mini band. And the exact Chern number depends on contributions away from the band touching. But we know that the sign of these will not change as we change the sign of D. So as we change the sign of D, we know that there must be a change of the Chern number by plus minus 3, which reflects the cubic band touching of the original ABC graphene. So you need a detailed calculation to figure out how this jump of Chern number is distributed between the two signs, and that's what we did in our calculation, and found that the Chern number is 0 for one sign of D and is plus minus 3 for the other sign of D. Now, it's interesting to ask about the Berry curvature distribution for either sign of D. So here's a plot. So the boron nitride is taken to be on top, and phi V is the potential difference between the top and bottom layer. We can think of that as the displacement, as a measure of the displacement field. On the side where the displacement, on the side where displacement field is assigned, so the Chern number is 0, you see from this plot that so the color represents the Berry curvature, and on the left, the blue color means negative Berry curvature. Oops, need to go back. So on this left, the blue color means negative Berry curvature, and the red color means positive Berry curvature. So the net total, the integral of the Berry curvature is 0, but there is a non-zero distribution of Berry curvature. Okay. On the right, we have a net Chern number. Now the scale has changed. Now both blue and red just mean refer to positive values of the Berry curvature. You see that almost everywhere the Berry curvature is positive, consistent with this non-zero integral, but still the Berry curvature distribution is hardly uniform, and this dark region, this big dark region in the middle of near the gamma point, more or less has 0 Berry curvature, while most of the Berry curvature is sitting somewhere else. Okay. All right. So what we learn is that for one sign of D, each Valley filtered band has non-zero Chern number, and so we cannot construct Valley symmetric linear functions. Now for the opposite sign of D, the Valley filtered bands have 0 Chern number, and there is no band topology. As I said, there are some Moiré graphene systems where there is no band topology, and we can play our usual games. So this is one. So then we can construct localized linear functions, but there's still an interesting feature that these linear functions are fat, because to accommodate the non-zero Berry flux density, so I said, even though it integrates to 0, there is a Berry flux density, which then renders a certain fatness to the linear functions. So we can model this system as a triangular lattice extended Hubbard model with 2 spin and 2 Valley degrees of freedom per site, but the fatness of the linear functions will change the structure. We have to refine what we mean by this extended Hubbard model. Okay. All right. So next, let me briefly discuss twisted bilayer graphene, nearly aligned with HBN. So here, so again, pristine twisted bilayer has these Dirac band touchings, and the near alignment with the boron nitride breaks the C2 symmetry and opens out gaps, and it gaps out the Dirac points. So for a simple understanding of what the resulting bands look like, let's use the continuum model and add the effect of the boron nitride as a perturbation. So one effect of the boron nitride is to give a staggered sublattice potential, because coming from the differences in the borons and nitrogen from the broken C2 symmetry of the boron nitride. Sorry, is there a question? No?
I think it was an accident.
All right, okay, no big deal. So this acts as a mass term for the Dirac fermion, so it gaps out the Dirac points. Now, there's another effect, which is that the weak Moiré potential from the substrate, the mismatch with the lattice mismatch with the boron nitride, gives a weak, incommensurate second Moiré potential from the due to the near alignment with the boron nitride, and potentially there's something interesting coming from the incommensuration between this Moiré potential and the Moiré potential coming from the twisting between the two graphene layers. As a first approximation, we can proceed by ignoring the substrate Moiré potential, because this is much weaker than the dominant Moiré potential coming from the twisting between the two graphene layers. Okay, so if we study the resulting band structure, so then indeed there is a gap between the valence and conduction band, and we can just go ahead and calculate the Chern number, and the two bands have the valence and conduction bands have Chern number C equals plus minus 1 as they advertised, and opposite for the opposite valley, this plotted for one valley. For the opposite valley, the situation is reversed, and the conduction band will have Chern number plus 1, and the valence band have Chern number minus 1. Okay, and this situation is described in these two papers. Okay, so the general message is that for many, but not all, flat band Moiré systems, what we need to understand is a problem where we have topological band structure and strong correlations. Now, we could ask, whether this is similar to Landau levels, which after all do have the special topological band and strong correlations. And the answer is maybe it is similar, but there are differences with Landau levels as well, which could change the physics, right? The most important difference is that these Moiré systems are time reversal symmetric, unlike the Landau level, where time reversal is explicitly broken. So it's roughly like a system with two sets of Landau levels corresponding to equal and opposite fields, which are coupled together by interactions, right? So that's one crucial difference. The other crucial difference, which actually hasn't gotten much attention so far, but is probably very important, is that even when there are Chern bands in Moiré graphene, as we just saw, the Berry curvature is not uniform within the Brillouin zone, unlike in the Landau level where the Berry curvature is just flat, right? And the third feature, of course, difference, of course, is that the bandwidth is not zero, and as we saw, can even be tuned in some systems, right? So there are all these differences with Landau levels. But despite that, in terms of if one way to look for precedent from other problems in solid state physics, it's probably the least misguiding precedent is probably quantum Hall than other situations. And if one wants to live on something else, living off quantum Hall is probably a better idea than trying to live off what we know about other solid state systems, right? But really, what I want to emphasize is that the problems posed to us by Moiré graphene, or to a large extent, mostly not like anything else that we've seen in solid state physics, right? So there's a nice slogan invented by Bhaskar that says that Moiré is different. So the thing to emphasize is that this is a conceptually new challenge for quantum many-body physics, and it's a meeting ground of these two active areas of modern condensed matter physics, both strong correlation and band topology. Okay, so with that, let's now turn to discussing the many-body physics in the nearly flat bands. So what we want to do is to project the Coulomb interaction to the active bands with some bandwidth W and ask what happens. Now we could try to proceed in the weak coupling limit, and in the weak coupling limit you will get a Fermi liquid metal with some weak instabilities. Now the effect of the Berry curvature might potentially manifest itself in some ways already in this weak coupling limit that hasn't been studied much in the literature. So one may be able to extract some indication of what may happen in interaction dominated phases already in the weak coupling limit, but that remains to be seen. Instead, let's now turn to the strong coupling limit and ask what happens. Okay. So I'm going to focus on total band fillings 1, 2, or 3. Say in one of these systems where the Dirac points are gapped. And this filling includes counting spin and Rayleigh degrees of freedom. Now, I want to make the case that in the strong coupling limit, that the natural expectation is that you get spin valley ferromagnetic order to fully fill a band and form an insulator. So this is a version of a phenomenon known as flat band ferromagnetism. But it's a special version of that more general phenomenon. And within the spin valley space, which kind of order parameter is selected is something that can be decided by Hartley-Fock. Okay, so let me give the reason why we expect this is true. Okay, and the basic physics is most simply explained by starting actually not with the topologically non-trivial band, but by starting with the topologically trivial bands of ABC trilayer graphene on boron nitride. So as I emphasized in talking about this, the band structure of this system, these bands are topologically trivial, but in momentum space, there is a non-trivial distribution of Berry flux. This means that though Warnier functions exist, they are fat, and they carry orbital moment. That's a physical way of thinking about why they have a minimum size. You can't squeeze in something with an orbital angular momentum down to become very, very narrowly peaked. So when we project Coulomb interactions, the Warnier functions at neighboring lattice sites, even though they're orthogonal, they are Mott squares, the Warnier densities have non-zero overlap. And like in atomic physics, this then leads to an inter-site ferromagnetic Hund's interaction in addition to the on-site Hubbard U. And this inter-site interaction is parametrically, it's of order U. So it's a, parametrically, it's a strong ferromagnetic interaction. So this then gives us a mechanism for ferromagnetism in a Mott insulator, which, where this ferromagnetism is set mainly by the Coulomb interaction, and it's not set by some delicate effect like what is known from the 1960s by this good enough Kanamori mechanism for weak ferromagnetism in a Mott insulator. Right? Question?
Yep, there is a quick question by Eric Suarez Morel. In the strong coupling limit where U is much bigger than W, the value of U should also be smaller than the distance in energy to remote bands?
Yes. That I'm taking that limit indeed. Yeah.
Mm-hmm. Okay.
Absolutely. Yeah.
Yeah.
Okay.
Was one question.
Is there one more?
No, this is it.
All right. Very good. Thank you. So we can demonstrate this very explicitly by constructing the Warnier functions and, carrying through this procedure, projecting the Coulomb interactions and getting a lattice model. So we did that. And so the interacting part of this lattice model, it looks like this. There's many terms. There's an on-site Hubbard U, there's a nearest neighbor, Coulomb repulsion. But the term to focus attention on is this term, which is the promised ferromagnetic inter-site Hund's interaction, which, as I explained, has its origin in the fat Warnier functions, and the fatness in turn has its origin in the non-trivial distribution of Berry curvature, even though it integrates to zero. Now, within this system, the estimate of this coefficient GH is small. It's about 1%, but more generally, there's no reason for it to be small. The point is that parametrically, this is of order U. Now, if you compare this with the standard super exchange interaction, which derives in perturbation theory in T over U, the super exchange interaction will be of order T squared over U. So in the limit that T is much smaller than U, the dominant magnetism will be ferromagnetism. And eventually, the super exchange will be able to compete with this ferromagnetism. And there'll be an interesting, such a function of bandwidth over U, there'll be an interesting evolution of the magnetism. Right? Okay. So that was for the topologically trivial band, where there's a very clear physical mechanism. Now let's turn to these plus minus Chern bands. And here we can make a heuristic argument first. And the heuristic argument is that for a topological band, say a plus minus Chern band, we can regard that as an extreme limit of this topologically trivial band with non-zero Berry curvature, where the Warnier functions are fat. The band topology means that here we have an extreme limit where the Warnier functions cannot be localized at all. It's not just that they are fat, they are infinitely fat. So this makes the ferromagnetic insulator even more stable. And here there's a useful analogy with the phenomenon of quantum Hall ferromagnetism. Okay. So then we can write down some very simple expectations for what happens at various fillings. At μt equals 2, which is half filling, we can expect that the weak intervalley Hund's interaction will lead to a spin polarized insulator. While at μt equals 1 or 3, in this limit, we can expect spin valley polarized ferromagnetic insulators. And once you're valley polarized, then fully valley polarized, then that means that one Chern band is fully occupied while the other is empty. This means that you will get a quantum anomalous Hall effect with Hall conductance of C times E squared over H. So it's these kinds of considerations together with Hartley-Fock that we used in our original paper with by Yahi, Pablo, and with Yahi and Pablo to discuss these, to come up with these kinds of expectations. Now, in terms of theoretical calculation to substantiate this, we can easily find these spin valley ferromagnets within a Hartley-Fock approximation. And that's what we did in our original papers, and that's what basically everyone else working in this field does, right? So essentially all the current theoretical work discusses this ferromagnetism within a Hartley-Fock approximation. But, you know, based on experience with, you know, other solid state systems, we have to ask ourselves whether Hartley-Fock is reliable, even in the flat band, in the strong interaction limit. You know, Hartley-Fock historically is well known to be notorious for overestimating ferromagnetism. Okay, so we need to, you know, if we are tough on ourselves, we need to not rest with Hartley-Fock, but we need to confirm these expectations by, you know, other kinds of reasoning, which to some extent is available in some of these systems. But really, the best way, perhaps, is to confirm these expectations with numerical calculations. So let me show you one numerical calculation that substantiates this this expectation of a ferromagnetic insulator. And this work by Cecile Repelin and Jihyun Dong, working with Yohee Zhang and myself. So the results I've shown here are results of an exact diagonalization calculation of various of these plus minus Chern bands. For instance, in twisted bilayer graphene aligned with HBN, or double bilayer graphene, or in ABC trilayer graphene. And indeed, and the exact diagonalization is done directly in K-space and ignoring the weak intervalley Hund's coupling. And indeed, what is seen is that the spin valley ferromagnetic insulator is the stable ground state in the strong coupling limit of the flat band and up to a finite range of W over U, finite, small but finite range of W over U. So, so there's 1 over the number of Moiré superlattice cells that she kept in the calculation. And the vertical axis is the critical value of the bandwidth over U at which you lose the spin valley polarized ferromagnetic insulating state. And you see that the numbers vary depending on, the critical value varies depending on which system you're looking at. But there's a reasonable, you know, there's about 10, typically it's about 10% of U. The system can tolerate a bandwidth of about 10% of U before transitioning out of this spin valley ferromagnetic, polarized ferromagnetic insulating state. Okay, so I don't have time to discuss these thoughts. This is just the spin wave dispersion, and this, maybe I should say a word. So there's an interesting effect of this on the spin wave dispersion of the distribution of the Berry curvature that indicates that the distribution of the Berry curvature actually might play a role in the physics, and that's something that should be understood more as we move, as we go into the future. So what we see is that in these plus minus Chern bands at integer filling, the insulator quite naturally will have some kind of ferromagnetic order, and at quite likely at half filling, we might expect a spin polarized insulator, at least if the intervalley Hund's interaction from Coulomb dominates. While at nu t equals 1 or 3, in the strong coupling limit, you get a spin valley polarized ferromagnetic insulator with the quantum anomalous Hall effect. Now, there is a point that I should emphasize here. In valley space, it turns out that for these plus minus Chern bands, valley polarization is favored over a different ordering that one could have imagined, which is inter-valley coherence. The system spontaneously breaks the separate conservation of particle number in either valley. In this limit, in a plus minus Chern band, it turns out the valley polarization, where the occupancy of one valley is different from the other, is strongly favored over this inter-valley coherence. So this valley polarization gives rise to icing-like ferromagnetism, which you can hope to detect, which you can detect in experiments by looking for hysteresis. Okay. So which then brings me to the relationship to experiments. Okay. So first, the spin polarized insulator at half filling. Yeah, Lima, is there a question? You're muted, Dima.
Yeah, we just have 5 to 10 more minutes.
All right, very good. Tell me when I should stop, and I'll just stop. Just
yeah.
a few
So
more
yeah, no. So I think we're in the question time, but if you spend 5 more minutes in the talk and 5 more minutes for questions, that should be fine.
All right, very good. So let me talk a little bit about experiments then, and that 5 minutes is just about right. So I'm not going to discuss the stretched double bilayer much more. Instead, I want to talk a bit about the spin valley, about nu t equals 103, where this, whatever the theory that I've described so far might lead you to expect a quantum anomalous Hall effect. And indeed, this is seen, a quantum anomalous Hall effect, and ferromagnetism is seen for twisted bilayer aligned with HBN and with in the valence band of ABC trilayer graphene. So the emergent ferromagnetism in this system was first reported by Goldhaber-Gordon and Mark Kastner. They saw hysteresis in the Hall transport and in the electrical transport. Not quite quantized rho xy, but nevertheless. And subsequently, in this paper by Andrea Young et al., which is now published in Science, and they saw a very nice quantization. Hysteresis is a nice quantization of RxY at a value of h over e squared, just like, so this is a quantum anomalous Hall state. Now, for in ABC trilayer graphene on HBN, for this sign of the displacement field, the Chern number is expected to be 0, and you don't see any hysteresis. Well, for this sign, the Chern number is expected to be non-zero, and at quarter filling, you see hysteritic transport, and you see a quantum anomalous Hall effect in very small fields, but with a Chern number of 2. And as I already discussed, that Chern number of 2 as opposed to 3 can be understood in terms of renormalization of the band topology from mixing the remote bands. So things seem to look good. And a lot of the literature looks as though people have declared victory over the quantum anomalous Hall effect in Moiré graphene. But I want to finish this talk by saying that I think we should take encouragement from this comparison between, from this convergence between theory and experiment, but I don't think we should declare victory yet. And the reason is that the strong coupling Hartree-Fock theory, has crucial features that are not tested in existing experiments. In particular, it assumes complete spin and valley polarization. And what the experiments tell us is the following. From hysteretic transport, which we only expect if for a discrete symmetry, we know that there is valley polarization, sometimes called orbital ferromagnetism. But spin is an associative degree of freedom, and we do not expect hysteresis due to spin polarization. And we do not know from current experiments what the spin is doing at all in any of the experimental realizations. We also actually do not know if the valley is fully polarized as described in this theory, or the valley is only partially polarized. Okay. Now, there's a very recent experiment, a nice experiment from Andrea Young's group, which used the so the measurement has, it's really interesting, but the measurement has some big uncertainties. Nevertheless, the measured magnetization is about 2 to 4 Bohr magnetons per unit cell. So this is bigger than the expected spin magnetization, and it clearly points to orbital magnetism, as also expected from the hysteresis. Now, the theory estimates of the maximum orbital magnetization is also of the same order as what's measured. So really, what this reinforces the conclusion that we can safely say that there is some level of orbital ferromagnetism, but we cannot say much about what the spin is doing, right? And this is something that needs to be clarified in future experiments. And theoretically, it's indeed possible to construct states of matter which are quantum Hall orbital ferromagnets, but are not spin ferromagnets, that will be consistent with all the existing experiments. So we have a couple of states that we constructed recently. One is a quantum Hall state where the valley is a ferromagnet, but the spin is an antiferromagnet. The other is an exotic state, really interesting, where it's a valley ferromagnet, but the spin is in a quantum spin state. So this simultaneously combines both the quantum spin liquid and quantum Hall insulator. And these states will all be compatible with existing experiments, and it's we'll see what happens in the future. And other people have proposed states with partial valley polarization, which might be consistent with the experiments, and so on and so forth. And microscopic theory doesn't give us too much guidance at this stage because experiments are not in strong coupling limit, and this is where the theory is safest, but we are at intermediate coupling. We are hampered by the fact that we don't quite know, we don't have a framework for dealing with strong correlations in a plus minus Chern band at intermediate coupling, and we have to see what happens in the future. So let me conclude the talk by discussing various suggested experiments that I think will be useful in the future. Be useful to understand how the transport gaps behaves as a function of in-plane field. We may learn something about spin physics. It will be useful to measure the magnetization as a function of the displacement field to learn whether the valley is fully polarized or not. And it'll be really interesting to study through STM domain walls in the quantum anomalous Hall state. I did something. So all of those kinds of things would be great to do, but we'll see. So let me then summarize. And so the two main things that I hope I've emphasized is that these systems are a new kind of theoretical problem in correlated electron physics. And there's a lot that we have to do both theoretically and experimentally to explore the physics. And there's encouraging convergence between theory and experiment for these ferromagnetic insulators. But a lot more needs to be done before we can be really sure, before we can declare victory, even in this quantum anomalous Hall state. So let me stop there. Thank you.
Okay, thank you very much, Senthil. So we will literally have 2 minutes for questions. So please write your questions quickly down if you want to take the opportunity.
Yes, that's sorry.
And what? Okay, yeah. So we have here a raised hand. Let me just. So we have. Just 1 second. Right. Yeah, we have a raised hand by Maximilian Kogel. I allowed you to talk.
Yeah, hello. Thank you for the talk. It was very good for the understanding. I have a question regarding the kind of transition from a Chern number of 0 to like Chern number plus minus 3 by a displacement field. I have a very hard time understanding that point because you're basically creating monopoles in your band structure by only a displacement field. Do you have a good explanation for that? It's very hard for me to understand that.
Yeah, sure. Yeah, very good. So in the idealized model that I talked about with the touching, happens is that at zero displacement field, you go through, let's see. No, I'm going in the wrong direction. Yeah, you go through a metallic point, right? So, yeah. So the displacement field is zero, then you go through a metal, right? But, so that's how you introduce monopoles, right? So you don't go through an insulator anymore. Now, in a less idealized model, so what happens in the real experiment, right? So real experiments, of course, you go through a metal, right? As you change the sign of the displacement field at neutrality, it becomes much less resistive. Where am I? Yeah, so this neutrality becomes much less resistive at neutrality, right? So that's really the point. Okay, there is an actual phase transition. If you wish, you're tearing the band structure apart and reconstructing it.
Okay, thank you.
Okay, so maybe we have time of one more question, so I'll just read it off. It's Chun Wu who's asking, how reliable are low energy field theories for twisted bilayer graphene? Same predicting transport properties. Okay, okay, I think you answered. Yeah, okay.
Yeah, so it's hard to know till one has a reliable,
right? Yeah.
A reliable low energy theory. Only then can we ask how reliable it can we calculate with that low energy theory to predict something. Right?
Okay, I think thank you very much, Senthil. It was very good overview talks. I think I also understood much more about these topological states now. If there are more questions, please send an email to Senthil. We take a little break and then we proceed to Jenny Lau, who gives the next talk. Okay, thank you very much.
Thank you very much.
Okay, yeah. So attendance was pretty good. So I think we had more than 200 people at one point.
Wow.
Yeah.
Yeah, sorry, I went.
No, don't worry. No worries.
Set up my time.
Yeah, no worries.
Yeah,
so we're just in time. So they were just in time. Okay.
Okay. All right.
Thanks a lot, Senthil. Thank you.
Thank you. Bye-bye.
Thank you, Senthil. Thank you, Dima. Thank you all. And we're having a few minutes break and we're coming back 4:30 with the next seminar. I'm going to end the meeting now.
Great. Thank you.
Thank you.
Bye-bye.
Bye.